Thank you very much. Thank you for the opportunity to present, and also, can you see my screen now? Okay. So welcome everybody. This session is now about ECoG and stereo-EEG hardware and software requirements. So basically what we need to conduct intracranial experiments, especially related to brain-computer interfaces. So here we can already see the definition of a brain-computer interface. So what we need is, of course, sensors attached to the brain or inside the brain. Then we have a unit to acquire the data and pre-process it, like filtering steps. We need a feature extraction module, and we need to make a decision. Okay, and based on that decision, we can send an output signal. So that output signal can then be utilized as a control signal, for example, to trigger muscles in the arm, to raise the arm here with electrical stimulation, or to communicate with a spelling matrix, to control a wheelchair, a robotic arm, or even a complete robot like this humanoid robot here. And important is that we don't utilize the natural output pathways of the body, but only the signals of the brain. So what kind of sensors can we use now to fetch the data or to read brain activation by means of voltage signals? So we can of course use non-invasive techniques like MEG or EEG electrodes. And then when we go here below the skull dura, then we reach the epidural ECoG electrocorticography. So we are reading directly from the cortex. Subdural electrocorticography, so these electrodes are already in contact with the brain. Then we have, for example, areas that are penetrating the cortex, like, for example, a Utah area to measure spikes. And then we have recording electrodes from deep brain areas, so depth electrodes or stereo-EEG electrodes. And these electrodes are usually placed through a screw hole in the skull into the brain tissue. And now when we compare the different recording modalities, we of course have different characteristics of the signal and measures of quality markers. So for surface EEG, usually we can measure roughly up to the mains frequency. So in Europe that is 50 Hertz, and in the US it's 60 Hertz. So usually until 40 Hertz we get good features or biomarkers from the EEG. Signal amplitudes that we record, depending if it's bipolar or reference to a more silent area like the mastoid or so, then we can measure around 100 microvolts amplitudes, and the sensors are usually roughly a centimeter, for example, a circular plate that is in contact, and the material is usually silver chloride because it has a low polarization voltage and can do an easy ion exchange, for example, with chloride ions with the sweat on the skin. Important is that we have a high temporal resolution, so compared to other markers like, for example, fMRI or fNIRS, the EEG as an electrophysiological biomarker is very quick in the changes. So voltage traces are changing frequently. The drawback of surface EEG is our spatial resolution. So here we cannot really discriminate between tiny regions on the brain, but get a very good coverage, for example, when we want to cover with the 1020 system or 1010 system the whole head. When we now come to the intracranial signals, then we can see here for the electrocorticography, we can also measure in regions of 200 Hertz. So the temporal resolution is in the same manner, but the signal to noise ratio is much higher. So we can also see in higher frequency components brain activity. Here is important to understand that if we look beyond main frequency, we are reaching the high gamma frequencies, and here we can observe broadband changes that are actually related to neural firing rate. So if you have an ensemble of neurons that is firing, we can see that there's a broadband lift of band power beyond the mains frequency. So this is a very useful biomarker then, for especially also when it comes to brain-computer interface research. Our spatial resolution is also much higher. So here we have contact diameters of roughly 2 millimeters, and the spacing between electrodes is usually 5 millimeters to 1 centimeter. And with, for example, matrices of electrodes, grids, we can then measure a whole area on the grain matter. In contrast, the stereo-EEG electrodes have similar properties, so similar impedances. Also, the material is the same, so usually platinum iridium is utilized for measuring intracranial biosignals. Sometimes also stainless steel is possible if, for example, we have intraoperative short-term recordings. For long-term implantation, which means up to 30 days in the context of epilepsy monitoring, invasive epilepsy monitoring, usually the platinum electrodes are utilized. And the surface of the electrodes, the impedance characteristic is rather similar, just the ECoG electrodes are more circular discs, and the stereo-EEG electrodes are cylinders with roughly 1 to 2 millimeters in size. And here we have about 2/3 of the sensors in the white matter, and about 1/3 of the sensors is in the gray matter. So how does these sensors usually look like? So for surface EEG electrodes, we can use gel-based or dry electrodes. So these are hybrid electrodes that you can see here. And in here we have usually dry recordings. So with this conductive polymer, we can measure the voltage signal from the scalp. And then if, for example, the impedance is very high, also gel could be added by reducing the impedance, and so making the electrodes less susceptible for artifacts and noise. The intracranial electrodes look a bit different. So here we have this grid with platinum plates arranged in a matrix. That's for electrocorticography. So standard electrodes usually have like 2 to 4 rows, and then like 4 to, let's say, 8 columns. This is already a quite big one with 64 channels. And then here, this is a stereo-EEG shaft where we have the electrodes at the tip of the shaft and then along the shaft with a spacing of a few millimeters, usually up to 1 centimeter. Okay, and then when we have implanted the electrode, we need also to connect them. So here you see examples from ECoG and g.tec. ECoG is from the US and g.tec from Germany. And usually these sterile parts, the electrodes, are implanted first. And then we need to connect with here this interface block. And then we have a connection to a non-sterile part. Usually these are standard connectors, 1.5 millimeter touchproof connectors, and then connect them to the interface of an amplifier unit. So usually a headbox is utilized for that. And this headbox can be a matrix like here of up to 64 1.5 millimeter medical safety connectors. And then we can already read the signal from the brain. Important here is that this whole signal pathway is completely passive, so there is no amplification on the way, and then at the amplifier we are analog digitalized converting the signal. So this works nicely if we have low impedance electrodes like here. For the intracranial electrodes we usually have like 1 to 5 kilo ohms. If we get much smaller in the contact area, for example microelectrodes or tetrodes, then at some point we will need also here a preamplifier as close as possible to the electrodes. But for a normal macro EEG or macro ECoG recording or surface or stereo EEG, this is usually enough to do it passively. Then there's also the option to avoid cabling montage time and also potential errors to directly connect to the headboxes with dedicated quick connectors. So we offer that also for different manufacturers of the intracranial electrodes to directly connect multiple electrodes with one cable to the amplifier. That saves time and also reduces errors. And that is especially helpful, for example, if we go up to 256 channels, or if we stack amplifiers, which we can also up to 1024. Okay, so now that everything is connected, we will go to the amplifier. This is now the G high amp. So here we have 4 possible head boxes that we can connect, each with 64 electrodes. And then we can see how the signal looks like. And here we have now from an intracranial electrode on the cortex to against the ground electrode recording, so potential change between the 2 electrodes. So the ground electrode here is now indicated as a scalp electrode. This is possible. We just have to be careful about any polarization voltage. So important to know is that, for example, our G high amp is a DC coupled amplifier, and with that we are measuring also slow cortical potentials and DC drifts. And the input range here is plus minus 340 millivolts. So if we now record from 2 electrodes, let's say from the same material, in the same environment, like on the cortex or maybe dural facing, then we will have usually a polarization or offset of about a few millivolts to 30 millivolts roughly. If we mix that, for example, with a steel electrode on the head, we can also see voltages from let's say 100 to 400 millivolts, and then this amplifier could in theory saturate. So what we could do is to apply an analog high pass, or to make sure that the ground electrode is of the same material in the same environment. Then we get this voltage trace here. And when we look at the spectrum of this signal, we can see this 1/f curve. So the signal intensity gets less with the frequency. This is also one reason why we cannot see high frequencies in the scalp EEG, because the amplitudes are already very tiny, and we are not reaching the electrodes on the scalp because of damping effects through the tissue layers, and then the signal is hidden in the noise floor. For intracranial recordings, we can still see also in these high gamma frequency ranges. And now when we look at the signal at different conditions, we can then observe that the signal changes in many parts of the spectrum. So when we overlay the 2 power spectra of resting condition and hand condition here, then we can observe low frequency band suppression and a high frequency band enhancement. So the low frequency suppression is usually an oscillatory effect. So we could see, for example, an new band suppression when we do a motor movement or motor imagination, and we can see that also on the scalp because it's very broad on the cortex, so the signal has a wide area, and also because of the frequency component is lower, we can more easily see it also on the scalp. When we now look at the same area in higher frequency bands, then we can see that some electrodes, but not the whole area, also show a very focal broadband increase. And this is now the brain activity that is showing us which neural ensembles are firing more frequently compared to the resting state. And this tells us that this area is now active because of the hand movement. So this is a task-related area, and this high gamma activation or broadband power lift has been observed first by the group of Nathan Krohn in 1998, and now more than 25 years already has been utilized for brain-computer interface research and also clinical applications, for example, for functional brain mapping. So I will show some exemplary brain-computer interface applications that can be utilized or realized with here ECoG sensors. So the group of Gerwin Schalk and Eric Luthard here at the Washington University demonstrated a 2D cursor control by means of high gamma features, showing that the patient was actually able to handle here motor imagery brain-computer interfaces with 2 degrees of freedom. That actually further developed to game control. Here we have the game Doom, where now the patient is controlling the avatar with a joystick, but actually is shooting by using the brain signal for oral movement imagination. And you can see that he's able to accurately trigger the firing of the gun. So this way, the group also from Gerwin Schalk could demonstrate how accurate a BCI trigger can be utilized in scenarios where the person is on high demand, controlling multiple parts and then adding, for example, gun control here. And with that video, they also, of course, got the attention of the US Army, because that is also something that can enhance use cases. Okay. Other use cases are to control a robot. So here we have a robot from a European project that was called VERE, so Virtual Embodiment and Robotic Re-embodiment. So that means that the goal of the project was to see and reflect yourself inside the virtual avatar, interact with others, or to even control a robot from first-person perspective. So here the patient was able to control the robot to lift a can. So here you can see the traffic light, and then the patient started to lift and then leave it again. And this concept should give us understanding that with the control of the BCI, we not necessarily have to focus on a lot of degrees of freedom with tiny movements, but also follow the strategy of context-related awareness. So also if you imagine that you want to grasp a can of Coke from the fridge, you don't think about how to grasp it, you just think about that you want to have it and that you want to take it. So you're grasping automatically. And the concept here is the same, that the humanoid robot already knows how to grasp the can, but with the BCI we just control the intention of the robot. So what do we need now to really do that? So we need, of course, an environmental scenario and a protocol to record brain waves and then label the data. So in order to label the data, we need to define a paradigm. So we need to define the condition in which the patient is while the recording. In the simple case, it's a resting state recording, but also it can involve some tasks. So for that, we are usually defining a paradigm. And also what we need to do is we have to record from the sensors in the brain, and for that we need a channel assignment. So we need to know which electrode from which part of the brain is a signal in our software here. So for that purpose we need a channel assignment. So then we know in each hardware channel of the amplifier how it corresponds to a software channel. Of course, all that happens on a control PC, and depending on the use case, you need a more or less powerful PC. Important is usually that if you go to a patient, and in most of the cases, recording from intracranial electrodes happens in the epilepsy monitoring while the patient is undergoing invasive seizure localization. And in here, you could potentially now record for a limited time. So in order to go with a research setup to this place, usually you would use a notebook, probably a more powerful notebook, for example, let's say with an i7 or i9 Intel processor, around 32 gigabytes of RAM. We usually operate on Windows 11. There are also like dedicated packages for Windows 11 where it runs on a low latency configuration, and then we can connect to the amplifier to record the signal. So the amplifier is connected via USB to the control PC, and the electrodes are connected via the headbox to the amplifier. And then after the patient has done the protocol and we have saved the data, we can now look at the data, how it looks like. So for recording the data, we usually use our g.tec. That is a high-speed online processing library in Simulink, so based on MATLAB. And then for reading the data, we can open it also in MATLAB, either natively, or we can also utilize the biosignal analyze software, GPS Analyze, for offline processing and visualization. So now here we can usually analyze the data, filtering, get features. And also what we can do is we can, with the HiSys, in online manner, process the data, so apply filtering steps and visualize features, raw data, interpret the signal quality, and also calculate output signals or feedback with the features. And examples have been like the BCI applications, but it's also possible to control other devices with that output signal, for example, an electrical stimulator. So with the electrical stimulator, you can give feedback, like we have talked about it for muscle stimulation, but you can also stimulate into the brain. And with that, you now are closing the loop to a closed loop neuromodulation system. And what you can do here is that based on the biomarkers, you could, for example, select the stimulation area with a switching unit and then stimulate into that area. So that can be, of course, be part of a research experiment, but it can also be used for therapeutic uses or diagnosis. So for diagnosis, you would utilize it again for functional brain mapping. So you would stimulate into certain areas of the brain and observe how the symptoms or the behavior changes during the stimulation, and can then by that associate to a function. Also what you can do is that you can, for example, stimulate into the brain to elicit seizures, to further diagnose or localize the epileptogenic zone. But it's also possible, for example, with stereo-EEG electrodes or depth electrodes to have stimulation for Parkinson's or tremor, to suppress the shivering or the shaking. And also, of course, it's possible to simply understand how mechanisms in the brain work in neuroscience experiments when you want to, for example, change the behavior or induce language, sound, speed, visual perception, or interrupt these circuities. The next step is to understand where the electrodes are located and where each signal comes from. So for that we can utilize our software q.tec, where we can topographically arrange our sensors. And here, for example, give a topographical label to each signal trace. And that also helps if we, for example, have similar features that are clustered to understand if they are in a similar region and by that belong together, or if this, for example, could be I don't know, volume conduction effect artifact that is just based on the geometry of the recording setup. Then the next step would be to improve that by a localization of the electrodes. So for that, we will need additional information from imaging data. So for example, MRI and CT data to co-register and localize the artifacts of the metal in the CT on the 3D brain based on a T1 weighted anatomical scan. And then we can also easily add fMRI results that may correspond with the electrophysiological markers, and also we can add tractography information. So we want to see how the brain activation is connected with fibers in the white matter. Okay, and to do that, what we need is a recording setup. So here we have the amplifier with the head boxes, the control PC, which for the recording at the bedside usually is a notebook, and then we also need a patient screen. That is important to give instructions to a patient and be able to still observe the signal quality and biomarkers if necessary. And if we want to have a complete stimulation and recording experiment, then we need a neuromodulation equipment that also includes the switching unit and the electrical stimulator to route and to the stimulation target and then apply the stimulation into the brain. So this package is also now certified in the EU as q.tec 2, and with that we have basically the possibility to record, and based on the recording then stimulate into the target areas to observe the symptoms, especially for functional mapping, but also to provide a platform for neuromodulation experiments. So how do we connect all this? So we have our sensors connected to the connector box, and then either directly or via the touchproof connectors go to the front part, the analog input of the switching unit, or directly to the high amp. And then here we have the stimulation output that also goes to the stimulation input of the switching unit and then back to the electrode. So all this is patient safe, so it's isolated from the harmful electrical primary part and also the secondary part. And here we have the applied part that is then safe in terms of the leakage current and the protection of the patient and the isolation. On the back side, we have the non-protected side, so to say, and here we can now also connect external devices and send and receive triggers. So this is based on the TTL standard. So many other devices also support that to send out TTL triggers. That is usually 2.4 to 5 volts as a high level. And you should send that sufficiently long so that the device can understand it. So for example, to trigger stimulation about 300 microseconds, or to see it in the amplifier to take care of the sampling rate of the amplifier. So if you have, for example, a kilohertz recording, you would need at least 1 or 2 milliseconds of trigger to sample that. Then also important is the arrangement for a clean recording. So usually all the analog input cables should be placed nicely to have no crossing of other devices or cables, to have no interference on the way to the amplifier. And then also we want to have the primary part and the power supplies on the backside of the devices, so that there will be like no interference from the supply side. And also in some settings it's possible to add a line isolator into the recording setup, so that the environmental noise or the mains interference is reduced as much as possible. Here is just important that we also need to separate that far enough from the analog input stage to not cause any EMC disturbances. Okay, and by that we will get a very high quality signal with low noise. It's also possible to have a parallel connection. For example, in the epilepsy monitoring unit, when you have a clinical monitoring system dedicated for localizing the epileptogonic zone, then you would be able to directly connect the electrodes into the stage of the switching unit, and in here split it into the monitoring system and also into the research system for a BCI experiment. And then you can also stimulate into the electrodes with the electrical stimulator, and with both recording systems record permanently. Okay, and yeah, there are different scenarios. It's also possible to completely separate both systems with a splitter box, and then have one signal path for recording and stimulating on the research side, and another signal path for recording and stimulating on the monitoring side. So depending on your environment and requirements, this can be easily handled to split the signal. Interoperatively, it looks a bit different. So usually we don't split the signal, we directly connect to the brain during the surgery. So for this, we need to connect passively here again to the head boxes, and then to the switching unit and the amplifier. Important in all these settings is that we have a good connection to an earth. So we need to be sure that there is like no big interference, as mentioned before, and that all the main supplies have a good earth connection to minimize the interference, and also that we have a proper ground and recording and reference recording connection. So here, for example, when we look at the epileptogenic zone, we want to place the reference and the ground recording as far away as possible to not fetch the epileptogenic signal, but still have a similar electrode signal compared to the recording electrodes to minimize the artifacts and interference. So for stereo-EEG electrodes, that can be, for example, a white matter ground, which would have the best signal quality, but also the risk of adding brain activity into our recording setup. And potential shift would be to have a subgaleal electrode as a ground. With this, we have a bit less noise compared to a surface needle and also less artifacts, but more noise compared to the white matter electrode. And the same for the reference, but here we also have the possibility to do a bipolar recording, especially for stereo-EEG, that makes sense, and also a single global reference in the subgaleal or white matter space is possible, or what also works is to have a common average reference, which is the routine technique for grid electrodes. So now let's look at the signal quality. So here we have now the signal only recorded against ground, and we can see that we can already mitigate our environmental setup by turning off other surrounding devices. So here this is a very clean recording as depicted before. And now when we enter the operating room with the same electrodes, we can see that here many other devices are surrounded and turned on. So therefore we already see a higher interference in the signal. So what we have to do is, of course, we have to select the reference to suppress the common mode signals and get the clean recording also in noisy environment. So you can see here, that's the ground against the reference channel, and these in the recording channels against reference have suppressed mains interference. So now what happens if we have no proper earth connection? We can see that the mains interference dramatically increases. So we need to make sure that this earth connection is given. So in some hospital environments, we have no protective earth in the electrical installation. So here we can use potential equalization, for example, of the ground of the notebook with the USB, and by that minimize this interference. Another important aspect is to make sure that the ground electrode has a very low impedance, because the higher the impedance of the electrodes, the higher is the interference effect. So on the left side you can see an impedance check that we usually conduct before each recording. And here you can see that many electrodes are in yellow, so 10 kilo ohms, sometimes higher. And on the right side, the majority is in green. So here we switched the ground electrode from channel 7 to channel 5. And by that, all the electrode recordings showed a lower impedance. Of course, the impedance is measured from each channel against ground. And with this impedance measurement screening, we can then optimize the recording quality to have the minimum impedance for the recording, and by that the minimum interference also. So here is it more illustrated on the actual raw signal. So here you can see some common mode interference that is then, after the changing the ground, gone, and the whole signal looks clean. So usually you have to connect the ground electrode to a dedicated plug. So in our headbox this is a yellow plug, but it's also possible, for example, to do that programmatically by means of the switching unit. So now that we have proper signal quality, we can now design our online processing tool. So we usually use the rapid prototyping platform in MATLAB Simulink called g.tec. And in here we can now have sampling rates of 1.2 kilohertz to 38.2 kilohertz with the input range of plus minus 340 millivolts, analog digital converted in 24 bits. So that means that we have 86 nanovolts resolution. And then we can choose if we want to have a DC coupled recording, which is very good, for example, for measuring evoked potentials like CCEPs, corticocortical evoked potentials, or if we just want to understand signal drifts over time, or if we are more interested in spectral changes, then we can also utilize, for example, recording with the AC coupled switching unit that has a cutoff frequency of an analog high pass of 0.16 Hz, so still good for evoked potentials. And then we can decide at which update rate we want to send feedback and update our features. So usually we do that with 150 Hz. So every roughly 7 milliseconds, we get an update cycle of our system independent of the sampling rate. And here we can already see an example block. So we have an amplifier block, then we have some spatial filtering, temporal filtering, variance estimation, then normalization of our features, linear classifier, for example, and then we get the probability for a decision, and then we can give a feedback based on that, and we can also store the signal and look at that in the raw data. So for each BCI experiment, we need a paradigm or protocol so that we can label the data and to understand what the person is actually doing and to train our decoder or decision making. So the protocols are usually written in XML language. So every task is here an entry as a tag, and then we can, based on the order of the tags, set also the duration for each task, and by that get the sequence of events and can annotate the label by means of markers. And also we can of course present, for example, images to the subject or to the patient. And we can also do that with simplification, the paradigm editor that helps us to, with a graphical UI, create this sequence of events. So here we have trained scrambled image against objects, and then we can preview that and see how the sequence is expressed for one example. So we can have, for example, here shuffled blocks of images, and then we can show that as a sequence. And each time there is a task switch, this event will be labeled and annotated in the EEG traces. So we will then be able to trigger trials based on the presentation events. To actually perform that experiment, to present and record in parallel, we can now go to the g.tec suite and here launch our g.tec, and from here we have a recording Simulink model where we can specify our amplifier path and also our paradigm path, and then merge the amplifier and the paradigm path to store the data and also to visualize it in this node, which is a raw data scope. So each block can either do a filtering or is a signal source like the presenter or the amplifier, or is a sink like the visualization scope and the save data node. So we can store the data of the EEG together with the presentation markers. And then here we can look at the individual windows that we can flexibly arrange and also add and remove nodes as we need it. And you can see here the high-pass filtered EEG signals together in parallel with the presentation. So this is the operator screen that shows us how long the experiment will last. And also we have a patient screen that can go to the patient monitor that we have seen before. And now the patient is looking at these images, and each time there is an image change, we get here this event ID changes in the presentation output, and that is now synchronized with the EEG data. After the recording, we have to look at our signals, if they are good and how the features are. So for that purpose, we can now go to the offline processing toolbox, the GBS Analyze, And here we can already see the recorded signal traces. So this is now the high-pass filtered signal. And the first thing we would like to do is to check if we see any bad channels or artifacts. And for intracranial signals, we usually have 3 markers for signal quality. So one are amplitude checks. So we want to see if there's any short-term outlier in the signal that can be caused by a bad contact, or for example by pulling on the cable, or big movement artifact, something that is transitory. Or we can also perform a correlation test or a line noise test. So the line noise test usually measures how high the interference is, and if we have a very high impedance, that also means that the signal quality will be very low. That will be shown by a very strong line noise feature. And the third one is a correlation test that will tell us if we have any open leads that we should anyway reject because there are no electrodes connected. So after the signal quality check, we can already see labels in the data so that it's annotated. So at the beginning we have the filter effect, so the settling of the filter. So all of these are like artifactual signals, but then it looks pretty clean. So we can take that signal. So when we now look at all the channels, we can also see that at the end there is one channel that is obviously in really bad connection. So we have some jumping signals and also a high interference in general. So we will annotate that as bad and exclude it from any further processing. This is also important because one way to reference is a common average reference. And with the common average reference, we want to exclude all artifactual signals or bad channels to not contaminate good channels with that bad signal. Okay, so for that we now select only the good channels and we subtract the mean signal for each sample from all the channels. And by that we further enhance the common mode rejection. So common mode signals like 50 Hz interference will be removed. And now that we have a good and clean signal, we can look at features that we may want to utilize for our experiment, for example for BCI calibration. So what we do, we now go on the presenter marker and trigger based on the marker. So we take a bit of a period before the actual presentation time, like 500 milliseconds, and then a sufficient long evaluation interval afterwards, like roughly a second or so. And then we can load the task information from the presenter. So in our case, we have several classes. So for example, presented faces, presented kanji characters, so Japanese characters. And also we have, for example, a black screen, which could be rest. Okay, and then we can look at time frequency maps or ERD, event-related desynchronization, synchronization effects. And for that we select the reference period, which is usually the period before the presentation happened. In our case, we are now screening from 5 Hz until 145 Hz. So we will see all the low frequency suppression and the high gamma activation already. And then we will calculate the time frequency maps for all our channels. Okay, and this is now a matrix where we get time frequency plots also by means of a heat map. And we can already see there are like some here red and blue blobs. So the blue blobs here are showing us an increase and the red one decrease. That means here we have a very strong high gamma activation and also combined with low frequency suppression. So this is usually the pattern that we are observing, for example, for visual perception. The problem that we have now is that we cannot really associate where it comes from and if all these blobs belong together or not. For that purpose, we are now creating a topographical montage. So we can utilize the Cortec montage creator for that. And what we have to do is we have to add the patient information, load the background image. And here we can already now place grid shapes or stereo-EEG electrodes on a background image. And with that, give the electrodes also a topographical meaning. So now we can place electrode shapes from a database. So all the big manufacturers like g.tec, PMT, Unique, Cortec, Dixie, Integra, and so on, they're in our database, and we can actually place the shapes of the electrodes and work with the spacing and the disc sizes and the shaft geometry. So when we utilize that, we get a better understanding. So here on the right hand side, you can see now a grid, and we can sort the time frequency maps, and we now see that this area is very active and is kind of a cluster on the cortex that is related to the visual perception here. So most likely this is on the ventral temporal cortex. And now we can calibrate our brain-computer interface based on the broadband changes that we have seen in the time frequency maps. So again, we can go into the GBS analyze and now see our signal traces again with the presenter information, and we will do a similar processing, but this time we are more interested on the high frequency components. So we will now filter in a high gamma frequency range of 110 to 140 Hertz. So for that purpose we are creating a Butterworth bandpass filter. So here we can see the frequency response. Give it a name. Usually it's better to use an anti-causal filtering for offline processing. With the MATLAB field option, we are filtering forwards and backwards to not cause any phase distortion in the filter response. And then we can apply the filter. So now our signal is diminished, and that is now the 1/f behavior that we can see that we mentioned before in the spectrum. So the actual high gamma values are much smaller compared to the EEG raw data that is more or less unfiltered. So here we can see that our strongest responses are in the range of 10 microvolts, and the average signal is usually like in the range of 1 to 2 microvolts. So what we can see here, there are some high gamma bursts that show us that there was some brain activity going on, and interestingly this is just happening after the presenter gave us the on marker for a presentation. So we will now trigger the data again based on the event markers. So now we can load the labels from the training run. So again, we have the faces, the kanji, and the rest. And now we can see on top the different colored labels from different trials and the corresponding high gamma responses. So as a next step, we are now calculating common special patterns that we utilize as partial filters to maximize the variance of one class and minimize the other. And then with that similar to a PCA, we can get a very strong signal to noise ratio of our features. I will now get a bit over this. So here what we can see is actually then the output of the features against the others by means of a linear classifier, an LDA, and we can already see that our high gamma responses that were even in the raw data, in the filtered raw data visible, are now, when we assign it to the labels, clearly distinguishing between faces and kanji. So when we now look at this in an online processing manner, we can see in the HISUS, after applying the linear classifier, we can run that model and we can see this is the input node where we load the data. Then we apply the bandpass filter for the channels, the spatial filter from the common special patterns, the decision-making part with the weights for the linear classifier, and then the feedback output. So this is our feedback window, and this is our feature scope. So these are now the spatially filtered EEG signals, and interestingly is that from like 180 channels, only 6 here are left. So these are the 6 channels from the CSPs that are class maximizing for class 1 and 2. So for class 1 are the first 2, then second 2 and the last 2. So for each class we have like 2 maximizing feature channels. And the nice thing of the CSP is that independent of the number of channels, which is not predefined for intracranial signals, we can always have like a dedicated number, a fixed number of feature channels, and can estimate and perfectly estimate our load for the real-time processing. So it will never run out of resources. And here we can now see if the features like here in 4 and 5 are met, then we can see the kanji. And otherwise, if it's in 1, 2, or 3, we can see a face. So now if we apply this into a real-world experiment, we can now see the feedback and hear the bell each time the patient sees a face or a kanji. And here we can again see the features when they are thresholded and the classification output on the screen. So that works for the printed faces and kanji, or for any perception in the mirror, the operator, and interestingly not so good for the doctor that was always in the field of view. Then we come to the next improvement, so we want to understand where exactly in the brain this activation happens, and for that we can utilize the EEG montage creator and co-register the anatomical landmarks with the artifacts of the CT. So it's possible to import any thresholded NIfTY, for example from SPM. What we usually do is that we import the output from FreeSurfer. So this is now the FreeSurfer output from a T1 weighted MRI scan of the brain, and then co-register it together with CT data. So here we have the pacillation information, and then we can load the CT data, co-register that, and after the co-registration we get in red here the artifacts that are aligned with the brain, and now we have to threshold the artifacts and get rid of any noise like the cables. Okay, and after that we can now get the electrode positions for each artifact, and then get here the electrode positions that are interestingly inside the brain. This is because of the brain shift, because when the electrodes are implanted, the brain is actually squeezed, and we have to correct for that squeezing part, because in the pre-surgical MRI the brain was not squeezed, but when we did the CT scan the brain was squeezed. And then we can project that and correct also for the actual shape of the electrodes. It's also possible to do the same for stereo-EEG. So either to place the shafts with the geometry from the database into target regions, or to also utilize the CT scan and then based here on the white CT artifact, take the virtual electrode and automatically snap it to the CT artifact or to the trajectory of the CT artifact. So here you can type the model of the stereo-EEG, and then this model will be assigned to all the CT artifacts, and each shaft can then be moved or aligned or replaced by another one. Okay, and then we can save that. So now that we have this information, we can actually look at the brain activation here. This is a recording while the patient was doing a grasping movement, and we can see here in the slice the brain activation in some gray matter electrodes in the medial part or in the reconstructed 3D brain. It's also possible to, for example, in HISUS, observe dead features that we also have seen before from the common special patterns, to just observe the high gamma in real time without any labeling. So here we can see the actual brain activation while the patient is doing the grasping in a single trial manner without any labeling, so we can see the burst of the activation. So when we utilize this signal now, and again perform the common special pattern and linear discriminant analysis, we can then follow the movement of the hand with the robotic hand. Okay, and also, of course, for the offline processing, we can now perfectly understand where our task-related changes in the brain happen and interpret them based on the, for example, anatomical landmarks. And here it is the fusiform gyrus. And then we can see that there is a strong phase perception on the fusiform gyrus, which is not present, for example, for kanjis. I think I will skip over that, but it's also, of course, possible to use that clinical for the purpose of functional mapping. So here, this is a study where we compared functional MRI with electrical cortical stimulation mapping and also high gamma features. And we can see that the high gamma features are co-localizing best either with ECS or with fMRI, where ECS was only working in 2 out of 5 cases and fMRI was oversensitive, showing a lot of false positives that are non-confirmed by other modalities. Another use case here is to show actual features, but now my PowerPoint got, I think, overloaded. Let me start that again. So now you can see that. So it's time to end, I see. So here we can also visualize, for example, during a seizure, the biomarkers. So here the seizure started, and then this is the high frequency band, and the high frequency band can then be plotted by means of RMS value, for example, or Z-scores on the brain at the time of the event, and that can be synchronized with the video EEG. So with the HISUS, we are very flexible to conduct online filtering, online feature extraction for different use cases, and then record, give feedback, or also, for example, stimulate into the brain. So here, this is an example where we, on the yellow sides, stimulate into the brain and then see the evoked responses that are very strong in the red bubbles. And the red bubbles are actually the area under curve of the evoked potentials that are caused by the electrical brain stimulation. Okay, and to sum it up, we have here our neuromodulation system, the Corteq with the electrical stimulation, the recording, the switching unit, the control computer to record and process the signals, and the patient screen. And with that we can do impedance check, EEG recording, channel routing, brain stimulation, and high gamma mapping. And on top of that, we can also do research applications for epilepsy, evoke potentials, and 3D mapping and closed loop modulation. All right, so yeah, I hope this gave you an overview what you have to consider when you do an experiment, and thank you very much. Sorry, Christoph, I'm just not hearing you. Yeah, but Christoph? I think Christoph is muted. Let's see if we can get connection. But it could also be on my side that my
Hello
audio
again.
now I can hear you, Christoph.
Magic recovery. So what's the difference between stereo-EEG and regular electrodes?
Well, I mean, stereo-EEG are basically also regular electrodes. When you want to compare the intracranial electrodes from depth electrodes against grid electrodes, then we have, in principle, the aspect that for stereo-EEG electrodes, we can reach deep brain regions that we couldn't easily approach without the surgery with grid electrodes. The drawback is that 2/3 are in the white matter. So with the grid electrodes, we have a very strong coverage of the gray matter. So it really depends on the indication. So for example, for a tumor surgery, where you anyway have to open the skull, you would utilize a grid to measure the entry point. And then when you go deeper, you would also try to measure maybe some white matter pathways. But when you want to, for example, localize epilepsy foci, then you could, with the stereo-EEG, just drill holes and not open the cranium completely, and by that have a less demanding monitoring phase. And also in theory, you could also utilize the electrodes then, for example, for radio frequency ablation to not even have the necessary operation afterwards. But that really depends on the use case. But other than this, the recording characteristics are very similar.
So Colin is saying most of the examples were involving the occipital lobe, but which other brain regions are you using as well?
Well, the BCI applications at the beginning, the majority was on motor imagery of tongue and hands. Also the robotic control was a mimic of actual hand motor execution. And in terms of, especially for functional mapping, language is very important. And for language, it's of course one aspect to stimulate into the brain to disrupt speech, and then by that understand which is the key part in the brain, for example, to understand or to generate language. And here also, of course, we get a lot of biomarkers that are language related, and many of speech decoding BCIs, of course, target if a person has problems, for example, by expressing verbally or overtly, then a speech prosthesis could also help to talk.
Another question is, are you using mostly one array or maybe 5 or 6 over different regions?
So in terms of useful re-referencing and source derivation, it's helpful to record at least from around 20 channels. So if you record from less, you will have problems by not contaminating other electrodes with re-referencing, or you really have a already predefined application where you know how to record, for example, with a global reference, like in a surface EEG setup. You would know that beforehand, and if you replace in an intracranial setup always the same montage, you could do that. But if you don't know what you have because you want to diagnose, it's better to have at least, for example, let's say 2 ensembles of 10 to 20 channels, maybe from different regions, and then a grounding electrode or strip or shaft that is distant, which could be white matter, subgilial, dural facing, and so on. But roughly like a grid with 20 channels or 2 shafts are necessary to get good signals.
Thank you very much, Christoph. So the questions are getting more and more, and I would like to ask you to answer them in the Q&A.